we're asked to show that 3 squared times 5 cubed has exactly 10 proper factors. Okay? Now we're told, if we don't know what a proper factor is, we're actually told this up here. Okay? It's just every factor of this number that's not itself or 1. Right? And, apparently there's 10 of those. And we have to show that there's 10 proper factors. Now, it's this number's written in a weird way, right? I mean, if we calculate what that is, I think it turns out to be this. Right? So it's 1,125. And we're asked to show that it has 10 proper factors. And it's written as the, product of its prime factors. So obviously we're going to use that in some clever way. But what clever way is that? Well, I was reading a book recently and it said, surprisingly, a lot of mathematicians don't really know how to count. They think they do, but they don't. Here, it's just a counting problem. We've got to count the number of factors. And in order to count, it's pretty simple. And, it's a combinatoric problem, a choosing problem. Okay, I guess once you have experience in these problems, it kind of see what to do. But basically, how many different ways can we choose a number to be a factor of that number? Well, I mean, we have two groups of numbers to choose from, right? You either have powers of 3 or powers of 5. Okay, so what powers of 3 can you have? Right, you can have either 3 to the 0 or 3 to the 1 or 3 squared. Those are what you can have. Over here, then with 5, you have 5 to the 0, 5 to the 1, 5 to the 2, or 5 cubed. And by some combination of those, we end up getting a factor. Okay, for example, if we choose 3 and 5 cubed, if we multiply those together, we have a factor. And that factor is going to be 375 or whatever, right? Okay. The idea here is there's 3 ways to choose a factor made up of purely 3s. And there's 3 ways to choose a factor made up of purely 5s. Well, 4 ways, actually, sorry. So if you think about that, the factors are split, with a dichotomy into 2 groups. And really, that's a cool idea. That's a cool way to do it. This problem is quite complicated, but if we make it simpler, how many ways can we choose numbers out of these groups? Okay, so in the first group, we have 3 choices. In the second group, we have 4 choices. So the answer is 3 times 4 is 12. There is 12 factors. Okay, so there's, 3 ways to choose the multiple of 3 in your factor, the power of 3 in your factor, and there's 4 ways to choose the power of 5 in your factor, giving me in total 12 ways. Now, of course, 2 of them we have to discard, right? Because one of them is 1, right? That's the 3 to the 0 times 5 to 0. That's 1, so we discard that. Then we have 3 squared times 5 cubed. What does that turn out to be? That turns out to be itself, so again, we discard that. So it's 12, then we take away 2, and we're left with, indeed, 10 proper factors. Okay? Then we extend that idea a little bit. So if we're given a number of the form 3 to the m times 5 to the n, well, if we want to find the proper factors of it, then, we can talk about, okay, you have 3 to the m, so really that's just m plus 1 ways to choose a power of 3 multiplied by n plus 1 ways to choose a power of 5. And then we subtract 2 from that. Okay, and what is the question there? We want to determine how many other integers have exactly 10 proper factors. So this is quite an interesting way to find factors, I guess. Now, what we're going to do here is we see that m and n must be integers. So m and n are integers, but they're greater than or equal to 0. So they're not necessarily like positive integers, they're just the non-negative integers. So they could be 0, which is interesting to know. Basically, we're just going to solve this equation by trial and error. Okay, a handy way to make this simpler right now before we start plugging different values of m and n in is if we move the 2 across, we end up with this equation. Hang on a minute. Well, isn't this kind of the same problem? If we think about 12, what is 12? 12 is 2 squared times 3, right? So actually, how many ways can we, well, how many factors does 12 have? We don't even care about proper factors. But again, there's 3 ways to choose the 2 and 2 ways to choose the 3. So 12 has 6 factors. Okay, so that's interesting. So, I mean, yeah, this question has enabled us to come up with an interesting way of finding the factors of a number. And proper factors, if we need to, we just subtract 2. So we see that 12 has 6 factors. Now, in order to solve this equation here for integer values of m and n, of course, they're going to be whole numbers. So each bracket is going to be a factor of 12. And there's 6 different factors of 12. So, we can list them. And really, for each of those, we'll have the corresponding value over here. Oh, sorry, no. What am I talking about? Yeah, 12 and then 6. Yeah, and it's just going to run down like that, right? Those are the values of m and n that'll solve the equation. So the values are 0. So 0, 11. Then what's this going to be? Yeah, so just going to subtract 1 each time. Okay. Not that difficult. But when you're recording yourself doing it on a video, it can be a little difficult. Yeah. Right. Yeah. Yeah, okay. I think that's right. Anyway, those are the values of m and n such that, well, the number will have 10 proper factors. Okay. So, so how many integers is that? I just wanted to know how many other integers have that form. Well, we see there's 6 others, right? But actually, hang on a minute, wasn't one of those the one we had in the first place? Yep, 3 squared times 5 cubed. So that was when m was 2 and n was 3. So there's 5 others. Okay, as long as we show it working out. If we've counted in that way, but we failed to count to 6, I think there might be a bit of a leeway for that, but let's get back up. All right. Okay, so let's again extrapolate this problem to be even harder. So n is the smallest positive integer that has exactly 426 proper factors. Okay, and determine n given your answer in terms of its prime factors. Geez, how am I going to do that? Well, it's going to be the smallest positive integer that has exactly 426 proper factors. Well, if we have any integer, it's going to be made up of the prime numbers in some way. Times 11. Right. I don't really know what these primes are going to be. So let's ... and let's times by p. I'd say the last one would be pn. So if we call these like p1, p2, whatever, they're all going to be to some powers. What are those powers going to be? How will we denote the powers? Well, I guess what's a good letter for that? I don't know, L. So let's say L1, L2, L3, L4, L5. You get the idea. And then Ln. That's denoting the problem. Now, basically, that number is our n, such that, what is we get here? So n is the... So if we have, well, this would actually be a set of numbers. But, you could say something like, if this is capital N, or we could say that that's a set of numbers, call a set S. It's like a set of numbers. And then, define that N is the min. It's the minimum value of S, such that, what do we want? we want the proper factors to be 426. Now, I mean, we take our ideas from here, right? Basically, you know, this had 12 proper factors. And if it had 12 proper factors, then that meant it had, well, if it had 10 proper factors, it had 12 factors in total. Which meant that if we added 1 to each of the powers and multiplied them together, we end up getting 12, right? So if it has 426 proper factors, it's going to have 428 factors. Okay. And when it has 428 factors, that means if you know, by our cool factoring method that we discussed, so n is going to be the minimum sort of number in that set, such that, I guess, L plus 1, so L1 plus 1, and then L2 plus 1. You know, I'll just do one more, L3 plus 1, and we're going to go all the way up to Ln plus 1, you know. And so it's the minimum such that this holds. Okay. Interesting. So it's a minimum s such that if you take all those L1s, and remember, you can pretty much represent any number by the product of its prime factors. So s could be anything at this point. We don't really know, especially because Pn isn't defined yet. But let's break down this problem. So we know that if you multiply everything, you're going to get, you know, if you multiply each of the, and by the way, these could be 0, right? I mean, for example, if I wanted to note, I don't know, let's say 52 as this number, what's that going to be? Like 2 squared times 13, right? Yeah. So, you know, number of cards in the deck, 4 13s, whatever. Notice, you know, I could write it like this: 5 to the 0, 7 to the 0, 11 to the 0, 13 to the 1, right? And then it would stop there. So that's how I would denote that number. So, you know, we pretty much covered every number. And basically, how do we choose our L's? That's the question now, right? How do we choose our L1, L2, da-da-da? So should we get the minimum number? Because, you know, there's different ways to do this. I guess it comes down to looking at 428 and thinking, well, you know, what are the factors of it, right? Well, let's break this down into the product of its prime factors. You know, we have 214, 107, so that's 107 times 2 squared at this point. Does 107 have any more factors? Well, 3 doesn't go into it. 5 doesn't. 7 doesn't. Does it? Does 7 go into it? 70 and then 47. No, 7 does not go into it. Okay, so near does 11. 13. So remember, we only have to check up to actually the square root. So actually, no, 107's prime. Okay, so we have this a prime number and 2 squared. That's kind of interesting, right? Which means how many factors does this number have? Well, it has down 3, so 6 factors. Okay, and so how many ways can we write this number? You know, as how many ways can we break it down? Well, there's actually more than you might think, because in order to choose the, okay, basically we know that n is at most going to be 6, right? No. Wait a minute. So you're gonna have to have that. Oh, this is a different problem, right? we have 107. Okay, and then we need to make this number 428 somehow. So I can't choose 107 to the power of 0, because then how would I make this number? So surely this has to be 1. Right? I mean, we have to have that, I think, somewhere. Yeah. I mean, so one of the L's, one of the L plus ones will have to be 107, right? Which means that one of the L's will have to be 106. Like it has to do that, or it might have, So this is, what are the possibilities here? So 107 times 4, or it's going to be 214 times 2, or it's going to be 428 times 1. Okay, I mean, I think we all agree here that the only way I can make the number is by doing it in this fashion. So how do I make that the smallest as possible? Well, by some rhetoric argument, I guess that 107 is going to be the smallest as possible. Okay, can you argue that? Because essentially, when you think about that, well, you can't have 214, because do you realize how much bigger that is? Like, think of it this way. If we choose our L1, L2, and L3 to be this is L1, L2 plus 1, this is L3 plus 1. I mean, we can't actually choose, so what would this number work out as? Right? I mean, that means L1 will be 106, L2 and L3 will be 1. So a number, actually, I think the smallest number turns out to be 2 to the 106 times 3 times 5. Okay, because if we chose any other number, any other value of 107, if we choose 214, that number is so much larger than this number, so this is going to be the minimum. Okay, I don't know how great my logic was at explaining that, but that was just me ad hocly trying that number. Question number 1. So that was a little tricky to think about, but there we go. That's my attempt at step 1, 2009, question 1. Hope you guys enjoyed watching me struggle at the end there, but I think I got there. I hope you guys can take something from that. So yeah.